Thank you all for being here. My name is Jan van Vegt. Before introducing myself, I'll quickly go over what we're going to talk about so that I can shape some context on why we're actually solving this problem. So first I'll talk a bit about the context, then I'll explain a bit more clearly, so what is the problem that we're solving. We'll go over the solution, and then if there's time, I'll talk a bit about after we've solved this problem, what kind of additional free benefits we're getting. Sorry, I'm a little bit ill as well. So, my name is Jan van Vegt. About a year ago, I started my own company called Composite, which is a platform for managing the machine learning models of our users. It's really been built with the idea that our users, which are data scientists, machine learning engineers, data engineers, should be able to do their job with as little configuration and as much flexibility as possible. Our users connect their Git repositories with their model definitions, how to get to their data, which metrics, etc., to our system, and every time they push code, we pick it up, and from there you're able to do experiment runs, deploy our models as scalable APIs, schedule batch jobs, retraining, etc. So, because we want to be flexible, we want our users to be able to define everything in Python, which includes getting the training data from any arbitrary system. To give a quick example of this was, for example, the data loader, and you can just choose your dependencies. In this case, it's an AWS S3 bucket, where they can download the data, or they define how to download the data. And this is the basic way to return that data to us, which is by passing two arbitrary objects, the features and the corresponding targets. Another way is to basically download raw training data, and then have another method that passes back a generator that iterates over this data, which is more useful for iterative models. By doing this means our users don't have to actually pass any schemas of their data. You can do that, you can pass those schemas, but because from a user experience perspective, if they don't have to, we don't want to force them to. So this is what my talk is about. We get these arbitrary Python objects that have some structure in them, and we want to be able to extract that structure so that we can use that in other parts of the process later. So that's our challenge. We have some arbitrary Python object that represents data. That data could be anything. That could be free-form text, it could be tabular data like a data frame or a Numpy array. Could be images, which are usually represented as Numpy arrays as well, but more dimensions. It could be time series data. And these objects, at the moment, in our system are the features, so that's the input of the machine learning model. Every row or every sample represents the input. Then there's the targets, which is basically the corresponding output, so what is the model trained on. And the third one is kind of the predictions. They're corresponding to the targets, but they don't have to be the same. In the case of a classification problem, you have could just be like an index for the class, while usually the output or the prediction of the model would be a probability distribution over these targets. So now that we've kind of established this problem, let's look at a quick example of what this could look like. So here we have a dictionary with a few keys. So there's a profile, which in turn is its own dictionary again, with the age and the province. So I'm from the Netherlands. So this province basically represents a region in the Netherlands. Then there's purchases with a list of different strings, which represent kind of things that maybe this customer bought in a supermarket. And then there's some kind of photo, which is an image. So our goal is, if we have a huge amount of these kind of samples, to learn what kind of the structure of these samples, so that we can use that in other parts. So to formalize this a little bit, our object represents some kind of iterable of samples. So that could be a list, it could be a generator, it could be a tuple, doesn't really matter. as long as we can kind of iterate it or maybe index it. These samples can have all kinds of different characteristics. They could be nested, they could have missing values or even missing keys. They can have very different corresponding types. And they can have variable length in them. For example, this list of purchases, it doesn't have to be that everybody has 3 purchases. So the challenge is to basically generate a schema, which is more like metadata, just based on these examples. So how are we going to achieve this? So we can start by inferring the schema for one sample. So this example that we saw before, we can try to map that to a schema. To do that, we're looking for a method or a function to be able to do that. And the schema here, it's with a capital because it represents some kind of object that we're building ourselves that represents this. And basically, these schemas can be of a lot of different types. There can be primitives, so these are just kind of the base, the unit Python types. This could be integers, floats, strings, and other ones. And you can have more composite ones, which are examples are lists, Numpy arrays, dictionaries, pandas series, those kind of things. I see that I messed up with the next slide, but so our goal is where we're going to, for this individual sample, we're going to look at parts of the sample and try to find which of these kind of schemas corresponds to that part or to the whole sample. So you can see some arrows already, they'll be useful soon. So in the case of the primitives, we can just look check for supported known types. And once we know which ones it is, we return the corresponding schema for that primitive. We can do this easily by looking at the basic Python methods that have a type or instance of, and there are some more elaborate ones that allow us to do some kind of introspection on Python objects that our users' code pass to us to be able to determine what kind of primitive we're talking about. Some examples is here, if we would get a 1, we can turn it into an int. If it's a string or a float, those are kind of easy to get. More interesting is to look at the composite side. We want our users to be able to express their data in a very flexible way. We shouldn't be, because they're using our platform, they don't need to be like, be kind of pigeonholed in the way that we're thinking about it. So we want our users to have nested structures, to have missing data, to use categories, things like that. So how can we do that? Well, the start is very similar. We have a long list of supported composite types, and we can just look at, on a sample level, look at a certain part of it if it's part of one of those supported composite types. Each of the supported composite types, we have our own schema class for it, which has some specifics to that schema, which has involving the metadata, maybe some children involved, but also some custom serialization and deserialization methods that allow us to be fast, and that's why the previous talk was also interesting for us, because we can handle a lot of data, but sometimes we want to do it faster. So this metadata that can be all kind of things that says something about the structure of that specific sample. And there can be children, which can have, these children can have their own primitive schemas, or they can be composite schemas as well. So there's a kind of a recursive definition of these schemas, which allows us to have these nested dictionaries with where certain keys have Numpy arrays, etc. And this recursive definition allows us to be very flexible in what it looks like. We'll go over a few examples of these composites because they can be a bit more tricky. So if we look at a Numpy array, it's a very common structure in data science and machine learning because it represents multiple dimensional data, and there's all is shipped off to C at the back end, operating on this using Numpy itself. can be very efficient. A metadata here is, for example, the shape, so that represents kind of the dimensions and the size of this array. And normally d-type would be a part of that as well. But in our case, the d-type is actually a child that this represents a certain primitive behind that. Usually those are kind of real primitives like a Numpy, float, int32, those kind of things. But there are also structured numpys where this could be another composite again. Another one that's very commonly used because it's very expressive are dictionaries. And in this case, metadata are the corresponding keys. So those are just basically the string representations of the identifiers of the values. And the children are then the corresponding schemas for each of these keys. So again, these could be composites or these could just be primitives. If we go back to our example, we have our 29-year-old person from the province of North Holland with some purchases and a picture that we took. If we want to map this specific sample to the corresponding schema, this is something that it would look like. So the whole sample is a dictionary with certain keys, and the key profile has another dictionary where the age is an integer, province is a string, and then going below again, the purchases is a list of strings, and the photo is, in this case, a Numpy array of 64 by 64 pixels with 3 color channels. So now we've kind of seen the approach to having one certain sample and turning that into a schema that kind of defines the structure of this sample. But our initial goal was that we have a large number of samples and we want to say something about the structure of data in general. So going from one sample is not enough. We're interested in basically having a schema of all these samples together. So to do that, we can take an approach where we basically take all these schemas and try to merge them into one schema. An example I will show here. So this is a smaller version of the previous one. We have the age as an integer, and we have a list of purchases, so that's a list of strings. And then we have another schema, which only has the age. So this one doesn't have the purchases. Up front, we, of course, as Kubernetes, we don't know that this is the case, so we basically try to merge these two together. So what do you think, how do we represent this? Because the age is still available in both of those cases, but all of a sudden the purchases is only in one of those cases. So this is, kind of turns into an optional one, or a nullable field. So if we merge these two together, we still have the age as an integer, but the purchases is a list of strings that is not available all of the time. So this is kind of, you could see this as a list of strings that is also nullable, if you think about it as a more database perspective. So this is kind of the base idea, where we first go to all these different samples and then try to merge them. So, perfect, another animation going wrong. So we basically take all these samples and we map each of these individual samples to schemas, these objects that we've defined that define the structure. And then we can reduce multiple schemas into one schema. Who is aware of the MapReduce paradigm that's used a lot in more distributed systems? Okay, so this is a very this is a very common pattern where you basically do a map, which is a one-to-one function from an individual input to an individual output, and a reduction is basically where you take two inputs from the same kind of distribution or same kind of space, and reduce it to a new sample in the same space. And so you could think about it, if you have a bunch of numbers and you want to square them and then sum them, the square is basically the mapper, where you take every number and you square them, and then the sum would be a reducer, where you take two numbers, you sum them, and you have a new number. And the nice thing about this is that it's very easy to distribute this. So you would distribute all your data over a bunch of different workers, and you can do that first a map can be very parallelized, and then the reduction can be parallelized as well by every worker reducing it to one number by themselves and then combining them and getting one final output. And that's something that we can actually leverage here as well, because we can start with, we can distribute all our data over different workers. They all map each sample to their own schema, and then those schemas can be reduced into a new schema. And that merging, that happens how we talked about before. If it's the same one, we just keep it the same, but if there's nullable, or maybe there could also be a union type. Let's say we have a string first, and another has the same key, but there it's an int. Then you could have a union over these two things. It depends a bit on how flexible you want to be. Maybe you want to raise an error there, like, hey, these are two kind of unmergeable types, but maybe you want to have a union. And again, if you the left and the right side are different workers, they first merge to one schema themselves, and then later you can merge those at a master level to have one defining schema. So now that we've been able to kind of achieve our task, we can use that schema. For example, in our case, we can use it to dynamically generate API of contracts to deploy those models for our clients without them having to specify any of these schemas. And we can also use it for better error handling. So if there's a new request being made for a prediction and it doesn't fit the type that we expected it to be, we can be much more clear about why we cannot make a prediction. And that's something we're working on now, and the next slide we'll talk a bit about more, is doing anomaly detection where you make a request, it has a viable schema, but it actually doesn't look like previous data. Then we want to be able to warn our users that maybe this is not a correct prediction. So I talked a bit about this free lunch that we're getting by doing this. Now that we basically have set up this whole architecture where you can go from individual samples and merge it into one schema, we can do more than just get the types. One of the examples that you can do is you can generate all kinds of statistics about what is happening. In the case of a list, you could talk about what is the length of each of these. And if you have a length of 3 and then a length of 5, you could say, okay, for now the average length is 4 with this kind of standard deviation. To be able to do that, to be able to use that kind of map-reduce paradigm, you need statistics that still fit in this scalable thing. And there's the min. It's very easy because the min you can look at two samples, just look at what is the min of these two, and keep that as the new minimum. Max is the same. The mean you need to do a little bit more effort where you keep track of the sample size as well. But there's even kind of these streaming algorithms for things like standard deviation. And keeping track of the number of missing values could also be relevant, because if there's maybe only one missing over 10 million rows, then maybe you should remove that one or flag that maybe that's not correct instead of making it a nullable thing. So I want to thank you for your time. If there's any questions, I'm happy to take them now.